We'll be looking at question 18, October 2020 paper. In this question is about the use of weak acids. In this case, oh, you got ethanoic acid as well. The student adds magnesium metal to aqueous solution of ethanoic acid. A redox reaction takes place. Write the overall equation for this reaction and explain in terms of oxidation numbers which element has been oxidized and which element has been reduced. So the overall equation, this is for ethanoic acid. So you've got CH3COOH. This is reacting with magnesium metal. You see the magnesium will lose its 2 electrons. And you've got your 2 ions there, CH3COO, and you've got 2 of those, because each one has a -1 charge. And you're going to have some hydrogen given off. And to balance, we just put a big 2 there. You know, hydrogen has gone from a +1 oxidation number to 0. Any element in its standard state, meaning it's only bonded to, an atom of itself, of the same element, has an oxidation number of 0. Anything diatomic or S4 or S8 or P4 or CO2 or O2 is 0 here in its standard state, and it goes to a +2. So what one is losing electrons? Magnesium is going from oxidation number 0 to +2 in MgCH3COO. It has been oxidized because it's lost electrons. What's been reduced? Hydrogen has +1 oxidation number in ethanoic acid and goes to 0 in, therefore, it's gained electrons, it's been reduced. We're using the oil rig to help us here. This question, student adds methanoic acid to ethanoic acid. The equilibrium setup is containing 2 acid-base pairs. Now, the thing is, you've been given the Ka values for methanoic and ethanoic acid. You've got the values here. How do you know which one is a stronger weak acid? It's a good question. You see Ka is equal to H plus and the remainder of the acid, negative ion, over HA, that's the weak acid. Now the thing is, the greater concentration, the more it dissociates, the greater the Ka value will be. So in this case, what's going to happen? This is the stronger of the 2 weak acids. Why? Because its Ka value is greater. So it says complete the equilibrium and label the conjugate acid-base pairs. Let's do the equation first. Methanoic acid, being the stronger of the 2 weak acids, gives off a H plus. That means ethanoic acid must be gaining. And what we do now, we label them. So let's call this is the acid one, and the base one will be on the right-hand side. What is giving off, what is going to be accepting a H plus out of these two? That's going to be the base, and we use the numbers to connect them together. The ones mean the methanoic acid and the methanoate ion. And so this makes this base 2, and the conjugate acid will be your A2. So these numbers are linked, and these numbers are linked. Use table 18.1 to answer the following questions. The student measures the pH and is given as 2.72 of ethanoic acid. Show that the concentration of ethanoic acid is this. So we know that Ka, this is for a weak acid, so we can substitute the top part. I'll just fully draw it out actually. You see, at the top part of the expression, we make the assumption that they are equal in concentration for a weak acid. And so what we can do, we can replace that with H plus concentration and make that squared. So how do we work this out? We're going to take Ka from the table, 1.78. 1.78 times 10 to the minus 5 equals, what's the concentration of H plus? What's the concentration of H plus? We're going to use 10 to the power of minus pH, in this case 2.72, and whatever the answer is, we square it and divide that by the concentration we're trying to work out. That completes the expression. So we can bring that up here and then bring that down there. So 10 to the power of minus 2.72, that gives you 0.905 times 10 to the minus 3. And we then square that answer and divide that by 1.78 times 10 to the minus 5. Yep, to 3 significant figures. .204 moles per decimeter cube. Oh, it's given the answer in the question. They just wanted to ask you how to do that. Okay, good. Moving on. Oh, this is a big marker here. The student plans to make a buffer solution with this pH from a mixture of ethanoic acid and sodium ethanoate. The student mixes this volume and this concentration of ethanoic acid with this volume of sodium ethanoate. Calculate the concentration of sodium ethanoate needed to prepare this buffer solution of pH 4.00. Okay. Now, whenever you're looking at buffer solutions, we always write down the expression. This is not a weak acid, so the conjugate base is actually from the sodium salt. That's the sodium salt. Sodium is a spectator ion. And we've got the Ka expression. Ka equals CH3COO minus H plus over CH3COOH. Okay, let's get all the values and start plugging them in. Up to here should make sense. And the calculations, there's a little bit more to what we're used to, but let's see. So Ka for ethanoic acid is 1.78. 1.78 times 10 to the minus 5. The concentration of the salt, this is what we're trying to work out. So let's highlight this. This is what we're trying to work out. Step to this after, which I'll show you. Oops. The pH that we need, so the H plus concentration, just a reminder here, 10 to the power of minus pH equals the H plus concentration. So what we do here, times 10 to the power of minus 4.00. That's the H plus concentration. And we divide that by the concentration of the ethanoic acid. You see, you've got volume and concentration here. So how do we work this bit out here? You see, for 1,000 converts it to decimeters cubed, multiplied by the concentration. This gives you the moles. That gives you 0.0816 moles. And you see 400 centimeters cubed and 600 centimeters cubed add up to 1,000 centimeters cubed, which is 1 decimeter cubed. So this moles that we've worked out is actually per decimeter cubed. So that's we've diluted it. That's why it gives you this concentration. So this value we'll plug in at the bottom here, 0.0816. And we can now work out the concentration of sodium ethanoate, but we need to do one little twist afterwards. So let's work that out. So 1.78 times 10 to the minus 5. Let's multiply that by 0.0816 and then divide by 10 to the power of minus 4.00. I've got here 0.014528 moles per decimeter cubed. Because the total volume is 1 decimeter cubed, where did we get 1 decimeter cubed? 400 plus 600, that's the total volume. We want the original concentration. So this is the total moles. So we then get 0.014528 moles and divide that by the volume, which is 600 centimeters cubed. We just convert that to decimeters cubed. That gives you 0.0, how many sig figs do I want? Let's just do 3, 0.0242. Did they ask for the answer in standard form? No, they haven't. Yeah, so the answer here is, yeah, 2.42 times 10 to the minus 2, minus 1, minus 2. Yep, that's acceptable. Up to calculator value. Yep, they've given their answer to standard form. Do you have to? No, you don't have to. That is perfectly fine, ladies and gentlemen. And I believe, oh, there's one more question after this. Not going yet. Yep, that's correct. So just a little bit of a twist here. So we worked out the concentration of the sodium ethanoate. So that's the overall concentration after mixing. What's the concentration of the 600 centimeters cubed that was added? So we need to divide that moles by 600 in decimeters cubed, which gives you the original concentration of that 600 centimeter cubed solution that was added. Hope that makes sense. Wonderful. I'll see you tomorrow.